Everybody, we're going to take a look at two new postulates today throughout this video. Remember, in our previous instructional videos, we've covered the definition of congruent polygons, the side-side-side congruence postulate, and side-angle-side congruence postulate. All three of those methods prove that two triangles are congruent, depending on the pattern of information you have. Today, we're going to cover two additional patterns. We're going to cover ASA and AAS. And what I have for you here in these two images is a bit of two starting points for triangles. These sides, BC and EF, are marked congruent. And then we have some measurements for you. Angle B is 62.42 degrees, is the same as angle A, 62 points. So they are congruent to each other. Angle B is congruent to angle A. And then we have angle F and C are both 67.08 degrees, rather, which means that since our measures are equal, those two angles are also congruent. So the starting point for our triangles, and I'll explain these dotted lines, is the angle-side-angle pattern. We are given a pair of segments that are the same, and then we are given a pair of angles on either end of each segment that forces us to put the line segments to complete the triangle in the same spaces, right? This 62-degree angle is directing me to put the line segment somewhere on this dotted line to construct a triangle. Same goes for this. So when we take a look at this starting point and we start to think about how many unique triangles can we construct with these starting points? Meaning, if I were then to complete both of these at least, what would the result be? Would the triangles be different? Is there a way to create different triangles given that we are forced to use these? And the answer is pretty clearly no. There is one way only to finish out these triangles, and that is to connect point C and just draw it down that line at point A, and then to connect point B and just draw it all the way down to point A, because the angles here on the base here on BC are forcing me to point these segments in this direction. So I don't have any freedom to move the sides around. The only ways that would give me freedom would be if I can change this segment length, which I can't because it's fixed, or if I can tweak these angle measures, which I can't because they're fixed. So I have one path I can create with this triangle. Well, it should make sense to you then. If I have the same exact path, even if it's reoriented over here, I can't come up with unique triangles. I am stuck here with the same two triangles that are congruent because this segment is fixed as the same, and the two angle measures on either side are pointing our remaining two line segments in both triangles in the exact same directions, which means that they will both have to meet in the same point, A and D in this case, which tells us that these two line segments are going to be congruent. And then if you look at it really quick, and we'll get back to this in a moment, this angle also has to be congruent because of subtraction. So we end up getting, just with this starting point, we get two triangles that have to be congruent because all of their parts match. This is the angle-side-angle congruence postulate. It tells us that if in any two triangles you have a pair of corresponding congruent angles, and an included side is congruent in both, or the included side in both is congruent, then the triangles must be congruent to each other. So let's move on to a discussion about why angle-angle-side works as a postulate. This is actually an enlarged version of one of your triangle congruence notebook pages, where I've taken this setup, this starting setup, to discuss why this postulate could work. And the way we're going to prove angle-angle-side is not going to be with new degree measures and imagining things existing. Instead, what we're going to do is we're going to leverage our previous triangle congruence postulate. I'll put that in the margin here. Remember that we've already accepted in this video that angle-side-angle must prove congruence. We're going to leverage this postulate to prove that AAS must also work. And now why is that? Well, let's take a look. These two triangles both have a pair of angles that are congruent to each other and a congruent marked side that is not included. So this is not ASA because the side is not in between the two angles. Instead, we would call this AAS, two angles with a side not included outside of it. Well, something we discussed back when we talked about the definition of congruent polygons was that if any two triangles have two congruent angles, then by the third angles theorem, the third angles must also be congruent. So if you know that you have a pair of angles in a triangle congruent that correspond, the remaining third angles must also be congruent to each other by the third angles theorem. And that's just by subtracting, right? If I knew this was 50 degrees and 60 degrees, that's 110 total degrees. And then if this is 50 and 60, that's 110 total degrees. If I subtracted both of those 110s, I have 70 degrees left for each angle. if the measures are equal, the angles are clearly congruent. And that is always going to be the case in all triangles because of that 180 degree angle total degree measure. So using that idea, we know that these angles are congruent. Well, now take a look, and I'll use blue because I highlighted this postulate on the side in blue. Look at what we have here. We have a pattern and postulate that we've already previously accepted is enough to prove congruence. This is the angle-side angle pattern, two angles with the included side. And we arrived at the angle-side angle pattern by starting with angle side and then just adding a step, the third angles theorem. Well, if you can get to the if you can get to angle-side angle by starting with angle side, stating the third angles theorem, and the side always ends up being concluded, then it's not really necessary to go further than angle side, because we know every single time we get to this postulate here, angle side, we are going to arrive at ASA by the third angles theorem. So this postulate here, AAS, is really just cutting out that middle step. It's recognizing that if we start with AAS, by adding the third angles, we're going to get to ASA.